Welcome back. Section 7 is going to be a lot, probably easier than the last few because we won't be doing a lot of what we've been doing with synthetic division stuff. There will be some, but not a ton. What we're going to be doing, we're going to be looking at graphs of polynomials and what makes the graphs do what they do. And so a lot of this is going to be conceptual as opposed to the computational stuff we've been really focused on recently. So, our learning targets today. I can use the properties of end behavior to analyze, describe, and graph polynomial functions. And then I can identify and use maxima and minima of polynomial functions to solve problems. Now, this last one is something we're just barely going to cover at the very end. But really, like maxima is just the plural for maximum, and minima is the plural for minimum. So we're just finding the high and low points. And that's going to be actually super easy. You'll enjoy that. So, first of all, graphs of polynomials. Polynomials have four distinct shapes to them. They can look like this. And yeah, there might be some extra like bumps and squiggles and stuff in the middle, but just overall, they can look like that. They could look like this. Same thing, bumps and squiggles. Can we see the difference here? Where this one, hey, look, these guys go up, and here they go down. They could also be going in opposite directions. Here it starts from going down and ends up going up, and there could be a lot or even no squiggles in the middle here. And could start out going up and then end up going down. And again, with a variety of amount of squiggles. We're not concerned today with really what's happening here. We're looking at the end behavior, which is what happens when x gets really, really big. I have a great method for remembering what these guys look like, but I couldn't figure out how to get it on here, and so you'll have to ask me in class. And to really be truly scarring, you're going to need to see it personally. And I also just want to see your reactions. I want to see that scarred, like break down to tears look in your eyes, just because that's the kind of guy I am. And I tend to pay for therapy for that, but that's okay. So, how we remember it we'll see later, but right now, we're looking at these. These are broken, I keep bumping my mouse. These are broken down into a couple things. These guys up here, where they're both going in the same direction, these functions have even degrees. They're even degree polynomials. Kind of like a quadratic, x squared, is an even degree. It starts out here, and it goes down, comes back up. Or a negative quadratic. These are actually x to the fourths. And then these guys are odd degrees. Kind of like a line. This one's a cubic. This one's actually a quintic. But they're odd degrees. Notice odd degrees, one goes down, one goes up. Even degrees, they both go the same direction. How do we know which direction they go? For that, we just need to look at the leading coefficient. So far we have looking at the degrees, and then looking at leading coefficients. Here, this looks like a positive x squared, where a is positive. And here it's a negative x squared, where a is negative. So this would be a positive, this would be negative. And then same thing here, positive. So these guys were looking at quadratics. Well, the ones down here, what's the easiest odd degree polynomial? Is it a cubic? Not really. It's actually a line. So how do we tell what's the leading coefficient of a line? Our line, y equals mx plus b. The leading coefficient is m. It's the slope. So is the slope positive or negative? Looking at this, I see it as a general positive. It starts down here and it goes up here. It starts here and it goes down here. But zoomed in this close, it's actually really hard to tell. And so I have a little video of my graphing software here where I zoom out. And so let's see what happens when we zoom out here. I'm going to zoom out and zoom out and zoom out. And see how this little blip here in the center, just disappears. Like it's not there anymore. Granted, we zoomed out and it went really close to the y-axis as well, so it made it pretty much a vertical line. But the important part is this blip doesn't matter. We start out down at the bottom and we go up to the top. It has a positive slope, so a positive leading coefficient. Then we can talk about the end behavior. The end behavior is just what's happening at the end. Each of these has two ends. They have an end when x gets really, really small. That's the left side. And an end when x gets really, really big. That's the right side. We're going to look at what happens to f of x, or p of x, depending on what they call it. What happens to the y value? So this first one here, we can look at as x is going to negative infinity. That means it's getting really, really small. That's this left side over here. F of x is going up. It's going to positive infinity. The only options for each of these are going to be negative infinity and positive infinity. Each one will have x is going to negative infinity and x is going to positive infinity. And then the f of x, is it going up, positive infinity, or down, negative infinity? I tend to think of it like this: as x goes to negative infinity, f of x goes to infinity. But the book switches it around a lot, and a lot of the questions it'll give you the f of x goes to blank as x goes to negative infinity. So I think it's going to be good to see it that way. It means the same thing. It's just which order is it. So f of x goes to infinity as x goes to negative infinity. Well, what about when x goes to positive infinity? F of x still gets really big, so it's also going to positive infinity. So as x goes to positive infinity, well, f of x goes to positive infinity. So we have these two statements right here. The f of x goes to infinity as x goes to negative infinity. F of x goes to infinity as x goes to infinity. That's describing the end behavior for this graph. And all that means is that when x gets really little, y gets really big. When x gets really big, y gets really big. So each of these will have two pieces of end behavior. We have as x gets really little and as x gets really big. So what happens? Let's start over here with the even degree. As x goes to negative infinity, y is going down, so y is also going to negative infinity. And as x is going to positive infinity, y is going to negative infinity. Notice with the even degrees, both ends go the same way. Positive infinities over here, negative infinities over here. With the odd degrees, we're going to have one of each. So here, when it's a positive leading coefficient, as x goes to negative infinity, y is getting smaller, so y is going to negative infinity. And then, as x is going to infinity, y is going to infinity. So this is for a positive leading coefficient odd degree. This is the end behavior. And it doesn't matter what those numbers are. If it's odd and a positive leading coefficient, this will always be the end behavior. Same thing with each of these. So going over here, as x goes to negative infinity, what happens when x gets small? Y is going to get really big. So y goes to infinity. And as x gets really big, y gets really small. So x goes to negative, f goes to negative infinity. So that's the end behavior of this. We're just looking at the size, and this can help us graph. So if we have an equation, describe the end behavior. Well, I can tell the degree, the leading coefficient is positive, because it's 2, and the degree is odd, which means it's going to look like this. If you follow the pointer, which I drew it, it's going to look kind of like that. A little sketch can help, because now we can see when x goes to negative infinity, y is going to get really small. And when x is really big, y is really big. And here it was p of x because that's what it was called. So it goes up. So we can describe the end behavior without ever having to graph it. And then same thing, if we have a graph, we can describe the end behavior of the equation. We don't need to know the equation, but from this graph, I can tell that it's odd degree because they're going in opposite directions. And again, I will scar you in class, and so you will be able to remember this. And then the general slope is a negative slope, so it has a negative leading coefficient. And so we can tell that about the equation just from the graph. If we want to graph a polynomial, graphing polynomials, we can use end behavior. And when we graph these, it's not going to be as exact as when we graphed quadratics, where we had to find a bunch of points, we had to plot the points, we had to draw it. No, the points, we're not going to find a ton of points because that would be a lot of points. We're going to find the important points. The important points are the zeros. And that's what we were finding for the past week. We're finding the zeros. So we're going to do the same thing. If we have a polynomial, we can find the zeros. Well, 48, with practice, I think, hey, -1 is a good one to try. So I'm going to try -1. So bring it down, multiply, add, multiply, add, multiply, add, multiply, add, and look, -1 works. Why did I think -1? Well, adding these two together gets us pretty much 48, but the signs are different. And so, hey, if we change the sign, maybe we get there. So I tried it. Look at that. And now, let's see, 28, that's almost half of 48. So if we take something close to 28 and multiply by 2, we might get 48. So let's try 2. Does this always work out? No. But it's a good guess. I don't have a calculator sitting next to me, otherwise I'd graph the polynomial on my calculator. But graphing it with by hand, and when it says graph, yes, you do have to do it by hand. Pretend you don't have a calculator sitting next to you. Try 2. So we bring down the 1, multiply, add, multiply, add, multiply, add, and we get 0. If 2 didn't work, I might have tried -2, just because it's still really close to times 2. Maybe it took it the wrong way. I don't know. Now we're down to a quadratic. So we have x squared plus 2x minus 24 equals 0, which we can factor into x plus 6 and x minus 4. X plus 6 means x equals -6. X minus 4 means x equals 4. We have some zeros here. We have 4 zeros. We needed 4 zeros. So we can get an appropriately sized graph, and we can put our zeros on the graph. Now with just end behavior, it's even degree and it's positive, which means our ends are going to be going up in both cases. We don't have any double roots, so it should come down, go through, so then it's negative, come back up, back down, and back up. And notice it ended up where we wanted it to end up. That's good. That's what it would probably look like. A good method of checking is to do what's called a sign chart, and this will be very useful in pre-calculus and really, really useful in calculus. A sign chart, I'm just going to write down the factors of this guy, x plus 1, x minus 2, x plus 6, x minus 4, and I'm going to plug in values in between in this range, kind of like what we did with inequalities, in our quadratics. I'm just going to plug in a number, like I can plug in -10. When we plug in -10, I'm just going to see, is -10 going to be positive or negative in each of these? Well, -10 plus 1 is negative, 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 negative. If I multiply 4 negatives together, I'm going to get a positive number. An even number of negatives will be positive. An odd number of negatives will be negative. So -10 will give me a positive number, which is what we should have based on our end behavior. Now let's choose a number in the middle and do the same thing. -3. Negative, negative, -3 plus 6 is positive, and negative. Now we have 3 negatives, which will be negative, which makes sense because we were expecting to go down here. Chances are the next one will be positive, so let's check. Plug in 0, that's the easy one. Hey, positive, negative gives us a positive. So we're going up here. And then plug in 1 in here, and it will probably be negative. And sure enough, there's 1 negative, so it's negative. And then finally, we should have positive. If we have a number bigger than these, we're going to have positive, 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 and we'll have a positive value. So we can use this to graph. We're going to be from here, just going to draw a line through the point, down below, then up here, then down below, and up again. And people always ask, well, how high does it go? Where does it, like, so you went from here to here. Like, why did you only go down to about -2? That's where my pencil went. I don't really care how high it is. I wouldn't even have the y-axis labeled. That's okay. The important thing is the shape, not how high it gets. And so, sketching a graph, look kind of like that. I would check it in your graphing calculator just to make sure, but it should look kind of like that. And so, then, lastly, to find the maximums and minimums. How do we find these points? Well, a teacher actually asked me this just earlier this year. Not one that works here, but a different teacher. She's like, how do we find the maximums and minimums? I'm like, well, using calculus. She said, no, without using calculus. We don't, because in calculus it's so easy. I don't think that a method was ever actually developed to find it without using calculus. And so, how do we do it? Well, to find the maximum minima, all we're going to do is use your calculator. You know that trace feature we used a couple days ago to find the intercepts and zeros? Do the same thing for the maximum minimum. About how high does it get? In the calc menu, there's also an option to find maxima or minima. It'll have you set your left bound and right bound, make a guess, just like with zeros, and then boom, you have your maximum minimum. That's all that we're going to do with finding it. In fact, it'll probably even say, find the maximum and minimum using your calculator. So don't worry about doing anything algebraically with that. That is all calculator stuff. So this is section 7. See how it wasn't really computational? Mostly it's just, is it odd? Is it even? Is it positive? Is it negative? And then what does that mean? Again, I look forward to scarring you when you get to class tomorrow, and I will see you then.